first of all, you need to because I just uploaded, due to my hassle in dissertation, I just uploaded in this morning. So in the Dropbox, there's folder called like day 4, and you can just only download just one file, Diffusion Theme Lab _2008. So did everybody download it, and did everybody open up the RStudio and open this file? It seems like it. So before going into deep in the course, so I think we might need some outline for today's lab. So today, please leave it up. So today we're gonna cover total 5 subsections of my lab. So first 2 will be more like epidemic model. So it's more like simulation geared model. So one is like SI model and SIS, and then using like epi model package. Then we go into more like empirical side. So we're gonna cover like peer influence model for opinions, which Jim might have covered in the morning's lecture. Then we use this foundation to. Okay. Yeah, that's fine. Yeah, thank you. So then we're gonna use some empirical data to estimate some network autocorrelation regression model, as well as QAP regression model, which leads to Jim's lab. So Jim will cover our ERGM model. So this is the foundation for that. So the 2 labs are linked this way. So for part 1, so I'm going to cover the static networks. Everybody can see it. So this is called SI model. So SI stands for like susceptible infected model. It's very simple. You can think of like the cold. So someone coughs, then you got infected, then that's you are infected. So we begin from this. So please library iGraph for this. And also, like, I have to mention about the motivation for this work, because for this we're gonna make it from scratch. So by far we only use some packages to do something like the tidyr, dplyr, and all the data management stuff. But for many kind of diffusion models, you need to build your own model, or you need to start from the beginning without any data. Then you have to use only basic code to construct your world. For example, like matrix language and calculate like different kind of properties. So you need to have some skills to make your own kind of world and model. So this is the very simple model that you can begin from here. So first we're gonna make a like toy tree-like network with 50 nodes. The size here 50. Then we use like graph tree function from iGraph to make the tree-like graph. So if you plot this one, so now we have like this little tree structures that each branch has just two children here. Then we're gonna generate some diffusion process upon this network. So then how do we do that? So we first initialize the diffuser. So we're gonna set the seed. The seed is only just one person. And this function is just the random number generator. And you choose with this sample function. So this sample function means that so from 1 to the number of nodes, here 50, then you're going to choose just only one randomly. Then because it's random, it might differ, but we set up the random number generator, so probably the same. So is it same? So I got 10. So the first infected person is number 10 person. Then this double bracket function means who is connected to number 10 person here. So in here, we have 5, 20, 21, 21st person. So let's make sure we have it right. Yeah, so we chose first number 5 person as the first infected, then this guy is connected to these three people. So that's how we know about the who's connected. Then we save it to the nearest neighbors object here. Then the next step is to set up the dyadic transmission probability. So you and I have a contact, and then you come to me, then how much likely that I get infected. So let's set that probability to 0.4. And this function, the sample, and the so sample is also like the choose the random number. But here I set up like 1 and 0 here. So among 1 and 0, and the number of these neighbors here, and I set up the probability here. So here's the probability is 0.4. So I pick up like 1 and 0 for these 3 person with this probability. And it shows that I pick up like this number, 0, 1, 0, for this person here. So number 5, number 20, number 21 has like this number. So I only picked up the number 20 person to be infected next time. Then I save it to the is.infected object. Then let's see. So here I end up selecting number 21 person for the next infected person. Then I combine, Then I combine these two into this object. So I got 2 person infected here. So this is kind of like basic process of this very simple model with only parameter for the dyadic transmission probability. Then also it's very easy to visualize. So I think you, by far, have only used like the StatNet or network package, but iGraph also does the nice job here. So what I did here is that, so let all the nodes color white, and I only colored red for those infected person. You see, so number 10 person first infected, then number 21 is next one. Then the next step is, so this is sort of like iterative process, right? So we can set up a function to make it very convenient for the next time. So this is all the function. It's basically the same thing, but it's just only store all the function to one kind of like the master function. So this is only choose like the nearest neighbors and choose a person to be infected next time. Then here the return all the infected person. Okay, then let's start the iterative process here. So I initialize a list for the infected like object. Then we're gonna save all the infected person's ID number to that object. So here, initially what we got. So I got number 6 person here. Then let's start the contingent process. So this function here is, so while we have all the people infected, we repeat this process over and over again. And this print function is very nice to get the sense of on what point that we are doing this process. So let's see. Oh, sorry. Yeah. Yeah, so you need to initialize I, then this function does the increment for the I. Then we can print out this thing. So what this function does is just continuously infect other person, and it gives like iterative iterations. So we have 22 iterations and 49% infected here from the seed. Then let's get the diffusion curve, which is just essential like property when you simulate the diffusion process. So using the apply function, we get the total number of count cumulatively. And pcom is just divide by maximum number, which gives us the rates. Then execute here. Then we have this kind of diffusion curve from the scratched code here. Then it goes. It infects every person as the time goes on. Then how?
Intuition-wise, that would be essentially a straight line diffusion curve. What's weird? That's right. What's weird about this graph that you wouldn't see, this network that you wouldn't see in a social network? It's a tree, right?
Tree, yeah,
so essentially what you're doing is at each time step, minus a random noise, because it's a coin flip, you're getting one new person and it branches, you get a little bit of bump every once in a while, but you don't have that kind of sinusoidal curve because you don't have enough redundancy in the network. It's just a tree that you're walking through.
Thanks, James. Yeah, so in real world, our networks are not like this, but it's just illustration purpose. So because every node only connected to 2, and that's the same structure for everyone. So we have just straight up curve. Then, so now we have the overall diffusion base in terms of visualization. Then how do we visualize networks? Because we have so many time steps. Then how do we visualize it? So for this, we first fix the coordinates. So every network graph have coordinates, so where the node is. So using this function, we fix the coordinates. So when you return L, so this is all the coordinates x and y for each node. And the first approach available is to just snapshot of particular time points. So the part function, you have already learned this. So this just divides this picture space 2 by 2. Then we're going to picture them just 1 by 1. And so this time, I'm just choosing just arbitrarily day 1, day 8, day 16, and the last day. Then you can visualize the snapshots in this way. The first day we had just only seed infected. Then it's just increasing over and over again. Then let's clear plot deck for the next visualization. So my plan was to have you get the GIF animation using this function, but yesterday I got some bumps. So I think some of you may have difficulties implementing this one. But instead, the alternative is to save each image slice to your computer, then combine them in a web-based software. So that's the route that we're going to take. And the function here is just we also while function to loop it over and over again. Then we save all the images that produces here to your computer. Then we're going to get them to a website to make a GIF. Yeah, so we created all the networks here. Then there's just don't show. But I think the course here has the website address, but you don't have to just go through all that. I'm just demonstrating. Yeah, here's all the file here. So we have 25 days here. And open. if you can here, like you can just choose the time between all the slice file. Then continue to decorate. So it's just all the fun because I know that in article you cannot publish like this kind of picture, but just for fun part, I'm sure like you're all exhausted, but
Published on one of the new open access online journals that some of us edit, you can publish something like this.
Or you can just hang it on your web page that I can do this, like things like that. Practically, yeah. So this is the animation that we created. Why it doesn't work? Oh, my computer just stopped. My computer just stopped here. Then Jim, maybe you just jump in to do this because I think the computer just got stopped. So maybe I can continue the later part.
Let's do a little switch around then.
It just stopped here.
All right, well, Jaemin's reconfiguring his machine. We'll just jump ahead to the stats model side of it and do that for a while.
Yeah.
And then come back. All right. So in the same Dropbox folder, there's another, in the day 4 folder, there's a second folder called Statistical Modeling or something like that. It should be relatively obvious. Grab that, and there's an R code in there that says randomization _ all or some such. That's the one you want. And for those of you that are like me and are afraid of doing anything truly live, there's also an R Markdown vision, so you can just follow along that way. This is also a wonderful example of it taking a village in that I couldn't get this darn thing to compile this morning, and then the Maria and the rest of the DNAC labs rescued me. So thank you to them for real-time editing. So that's awesome. All right, so we talked this morning a bit about running statistical models and networks, and the basic idea was that we're going to compare the graph we have to a series of random graphs that do something that we care about, that make a sort of a reasonable comparison. And so, all right, so the way we're going to work this, sorry for the delay. So we do, the front end of this is exactly the same as the last couple days that we've been working with. We're going to load up the ad health, the little pseudo ad health data. For those of you that were wondering about this when Kathy was talking, this is not the real ad health data. So this is the ad health data that we've stripped all the identifying information out of one, so there aren't even the same numbers that are in there. And then all the variables have a P in front of them. That means pseudo. So we made up that data. So we made up the genders, we made up the grades, we made up the smoking, and you'll find that a lot of these models fit really well. They fit really well because we cheated, right? Yeah, who knows, right? So if you're trying to fake data for a journal article, you wouldn't do it this poorly. But it does make for a pretty significant test in an example like this. So what I thought I would do is walk through a couple of the standard things we just talked about today. We talked about over the course of this morning. So we're going to read in, the first thing we're going to do is going to read in our data set like we did last time, just however you happen to have it, set your working directory, pull it all in. When you get the data in, well, we're going to collapse it down again from the full base data set to just the data set for the first community, select out just the variables we need, including grade, sex, the pseudo-smoking, and the community variable. We're going to pull that into an edge list, and then from an edge list, we're going to pull it into a graph. And so we're going to start today using the StatNet program and the SNA tools to generate random comparisons to the graph we have. So you load it up, you get all the acknowledgments, you see what's happening there. Goes and goes and goes. This is how StatNet assigns attributes to the graph, right? So we have a graph called G as network from our edges. Again, I was a lazy person. I didn't tell it was 71 nodes. And I gave it grade, sex, and smoking. I also, I'm later going to want to do some of these row and column effects that I told you about this morning. And so ahead of time, I created an out degree attribute, an in degree attribute, and a total degree attribute, and just added those to the graph. Just to check to make sure that nothing looks completely stupid, right? This is what the graph looks like if you were to, I'll just zoom in here a little bit. And so this is what the graph looks like, just to make sure it's clustered by grade. The reason I always do this, just so you know, is I've randomly sorted things wrong so many times in my life that when I know something's true, I want to look at it and make sure. So if I plot this by grade and see that the 7th graders are all over the damn place, then there's probably a problem and I'll go back and fix it. So it's just a sanity check, right? Just to make sure that you haven't done something that you know is stupid and you don't want to do. Gender, of course, is harder to see, in part because I should have recoded it instead of 0 and 1 and the colors are bad. But we expect a little bit of like, here are some red nodes connected together, here are some black nodes connected together and such. And so just to make sure that it doesn't seem completely ridiculous. And so the first thing we want to do is just a bivariate comparison. Are the observed statistics in our graph something like what we would see in a random graph or not? And so let's just take something like the transitivity ratio. So the transitivity ratio is just the number of two-step paths that are also one path. So for all possible cases where A is a friend of B and B is a friend of C, you ask the question, what proportion, that's your denominator, so what proportion of those sets is it also the case that A is a friend of C? And in this particular school, that's true 37% of the time. So 37% of those two paths are also one paths. Is that a big number or a small number? No idea, right? Compared to what is the obvious question. There's also in this case, well, we know some things about it. We know that out of the 71 nodes that are there are 71 times 70 possible dyads. Of those number of dyads, 85 of them are mutual, 135 are asymmetric, and 2,265 are null. So that's going to limit the number of those two paths we can have, right? So if we know what that distribution is, that sets a fundamental limit on the number of two paths that we can have closed, right? So these mutual ties, for example, are going to constrain the number of triangles I can close because that density has gone to another mutual tie as opposed to opening up to close the triangle. So let's simulate some networks that match on this dyad distribution, but everything else is random, and see if the dyad distribution can account for the amount of transitivity we see in this graph. And to do that, we do a little loop, and so I've set up some code here. You can see this exact same code later. The fact that you can use the exact same code in multiple spaces, when you find yourself doing that, what you should do is write a function, right? I didn't write a function because I was lazy, and I just copied and pasted. But if you're a good person, a better person than me, you would write a function that is, simulate, and you would just have this process go through. But this is such a simple bit of code that it wasn't worth to me anyway to do. Excuse me. For the novice programmers in the room, there's a couple things that that we're doing here. So this is just a loop, like Chris talked about this the other day. So we're going to take something, we're going to start at one spot, we're going to do it some number of times, in this case 500 times, and we're going to sort of stack into a vector the results that we're going through. And we're doing a while statement. So we're saying while this j, this index number, is less than the number of simulations that you want to do minus 1, we keep doing the piece. I personally almost never use while statements when doing a loop. Because in this case, the thing that we're conditioning on is a fixed feature that I'm iterating every time, so it's unlikely to fail. But often you'll do something like do while, your triangle has 4 sides, right? You'll do something that's a stupid thing that's impossible. You'll set it up, you'll set it to run, and you'll sit and watch it for a month, because it'll never converge, right? Because you've done something stupid where the internal that you reset a variable or you do something inside your loop that's going to make this condition never come true. Right, so it's always, if you're writing code for production purposes and you want to make it work, you always want to have an exit somewhere so that you know that if it's looping for a long, long time and nothing's happening, to bump out and say, are you sure you want to keep going, right? So a good code would do that. So this is not good code. This is effective code, but it'll get us where we need to go. So functionally what we're doing is we're just saying for each of 500 times, we're going to create a random graph from the uniform mutual asymmetric null distribution. We're going to pull one draw from that random graph, from a graph that has 71 vertices, that has as many mutual ties as we observed in our graph, as many asymmetric ties as we observed with our graph and as many null ties as we observed in our graph, right? So we're just setting this up to be, to pull from this distribution fixed on that set, right? And so that's one random draw. We pull that random draw. We calculate the transitivity for that random draw. We put it into our stack that we initialized up here. And if that didn't return a null value, we add one more to our index and do it again, right? So that's all this loop is. Because this is a simple calculation, this is always true, so we're just going to do this 500 times, right? So that just happens. You run that little code. Then we're going to go through and plot it as a histogram, and this is what you get, right? So this is the distribution of the random scoring. This is what you would expect to see under chance given the distribution of dyads. And this, way over here in New York, is what we would expect to see in our observed case. So it's exceedingly unlikely that our graph is a draw from the random distribution of graphs conditional on the number of dyads. Couldn't possibly generate that level of transitivity, right? So good. We know it's not the dyad distribution that's driving it. But we also know this is a grade network, right? And it's highly clustered by grade. And so if you do what's called a mixing matrix, which is just a crosstab of the ties from 7th graders to 7th graders, 7th graders to 8th graders, 7th graders to seniors, right? We see this is highly clustered down the diagonal. And that clustering down the diagonal means that 7th graders actually have very high density with other 7th graders. And that kind of clustering makes it very likely that you're going to get closed triads. And so it could well be the case that the transitivity we see in this graph is induced by the fact that people aren't actually finding friends at random in the graph, but only from the much smaller subset that they had to choose from within their own grade. So what we'd like to do is generate a random network from a distribution that holds constant this mixing set, right? So we know that we get the same set of mixing, we hold this constant, and do we find any transitivity above and beyond what we would expect from that? Now what you should be able to do is go through and do this exact same loop we did above, but remove that random mixing for the uniform mutual asymmetric null distribution and just do the random graph from the in-mix distribution, which is an arbitrary mixing probability. I couldn't get this code to work. I couldn't get this code to work in two ways. I could get it to produce. If you take grades and change that to as.character grades, it'll work. It'll actually produce something that looks like it results, but it produces a lot of empty graphs. So there's still something wrong in the pull from it. So we're going to skip that, and we're going to do it the old-fashioned hard way, which is we're going to generate the underlying distribution by hand by first generating a probability matrix the same size as our network, and then doing a Bernoulli coin flips on that probability matrix. And so to do that, we have to go through a couple steps. The first things we need to do is to translate our count mixing matrix up here. This is the thing we created right here, which is just the tie accounts table, to something that would make sense from a Bernoulli coin flip point of view, right? So that means we have to turn each of these into a probability on the edges. And so that means we have to divide this 52 by the number of times 52 could have happened, right? And so we take how many ties are possible between 7th graders. We observe 52, divide that by the number as possible. That gives us the probability of observing a tie amongst 7th graders. And to do that, we can create a little table. I should have printed this out. This is just the number of people in each grade. So that turns out there are 15 7th graders, if I remember correctly. And so we can then say, just treat that as a matrix. And then we just do the matrix multiplication of one by the other, and that tells us the number of possible cells in each case, right? Go ahead.
How do you choose what parameter or like transitivity? Why did you?
I just picked that one at random because it calculated quickly. Yeah, that was it. So we actually, sociologists didn't care about transitivity because it's a marker for it's a friend of a friend is a friend theory. And so we know that that's a characteristic of human networks, for example, that we don't see in chimpanzees, we don't see it in baboons, we don't see it in other kinds of social animals. And so it is a marker for human sociality, is that we care for what other people do, respect in terms of its third party. And so it's interesting in that sense. But to be completely honest, I picked it today because it was fast. Right. And so, but the idea here is that you could substitute out transitivity for anything else you care about, if you have a statistic you care about. Go ahead. Oh, yeah. Absolutely.
Some people are like having their fingers like
don't let your fingers bleed. Come on, man. I've got 4 cups of coffee and a brownie in me, man. I'm ready to go. All right. So the logic here that we're trying to do is to generate an underlying probability matrix for the network. And in order to do that, we have to build this up in pieces. The earlier code I gave you did that under the hood. What this chunk of code is doing is spelling out in the steps how you would actually go through doing that. And so to do it, what we do is we first take this count matrix, we divide each cell of that count matrix by the number of possible ties that could occur in that count matrix, and that gives us a probability of observing a tie from a 7th grader to a 7th grader, from a 7th grader to an 8th grader. And so what's the probability of observing a tie in a tie accounts matrix? Well, it's just the number of ties divided by the number of possible ties that could be there. The number of possible ties from 7th graders to 7th graders is just the number of 7th graders squared, right? Now, that's not exactly right, because we should be forbidding self-loops, but I was too lazy to look up the code to figure out how to subtract 1 from this particular case. And so I just took the square of all those cells and called it good enough. So we're going to be a little bit wrong. So again, if you go to production code, figure out how to fix that part. But the logic here is just that we now have a probability matrix where each of these cells tells us the likelihood of finding a tie here. And we see that it's very likely if you're in 7th grade, you're going to tie to other 7th graders. In fact, 52% of ties from 7th graders fall into 7th grade cells, right? So we go through, do this matrix, pull it out, right? And now the next step is to blow that little matrix up into a full 71 by 71 matrix, because that's how big our network is, right? And so what we wanted to do is, logically, we now have an adjacency matrix, right, that is empty. It's full of nothing. And we want to translate that empty adjacency matrix to an adjacency matrix where each cell is the probability of that edge being on or off. The only information we have is the grade of the row and column of that cell. So what we do is we go through and we compare the row and column grade that we observed of I and j to this value here, and we map one onto the other. So all we're going to do in this next set of codes is it's a lookup and mapping process, right? So we're going to go through that 71 by 71 matrix. You could do it as dyads if you wanted. It doesn't really have to be a matrix, but it's just the logic is clear this way. And you're going to go through and say every time I see a 7th grader and a 7th grader as I and j, I'm going to put 0.52. If I see an 8th grader and a 10th grader, it's going to be 0.016, right? So I'm just going to walk through all those cells and make sure that happens. Now, of course, you don't want to do 71 times 72, so you don't go through and do that entirely. Instead, what you do is you go through my probability matrix, which is this thing up there instead, this 7 by 7 matrix, and I say, well, let's find all instances in the network where it's 7th graders to 7th graders, all instances where it's 7th graders to 8th graders, all instances where it's 8th graders. There's just fewer steps you have to go through in the loop. And that's what this code is doing. So I'm going to say for all I in that little probability matrix, for all j in that probability matrix, identify the spot for which the grade is equal to the values of I, right? So this is just a lookup case, another lookup case, and then I'm going to map in the value in that cell. So this is just a way of doing that mapping. It's just going to go through and do that mapping from cell to cell for us. And now what you have at the end of the day is this little probability matrix now is going to be the thing that, is that right? Make sure I got the right one. Yes, so the probability matrix there is just the 71 by 71 matrix, so it's an adjacency matrix, the value of which is the probability of a tie on that edge, if we're just looking at the grade distribution. So that's all we're getting out of that set. Again, I'm going to run 500 iterations of that. I'm going to pull it off of the vector, sort of to initialize my overall set, and then do the same kind of while loop. Right? We do it, it generates it, and we get this distribution. Right? So now we're still much more likely, we see a higher transitivity in our graph than we observed by chance, but not nearly as much, right? So the mean here is now about 0.2 compared to what it was before, is just over 0. Right? So this tells us that a lot of the transitivity we see in this network is being accounted for by the focal organization of the school. That the fact that these schools are putting kids in grades, kids are next to each other, they form friends with people who are available to them. That's a much smaller subset than the universe of all kids in the school. And so that then makes it possible to get a lot more closed triads just by random chance than you would see otherwise. Right? So this is why it's important to think about these conditioning features. The fact that I don't ever bump into a lot of really cool, rich, popular people means that I don't have lots of real cool, rich, popular friends, but that doesn't mean that I have an avoidance of them. It means I just never get the chance to meet them. Right? If I had the opportunity, right, off I would go. And so this is what we're trying to do here, is to figure out what are the features that are constraining the network that we can fit for. And the logic, just so if it wasn't clear this morning, the logic of this kind of modeling is that if I can identify the right set of features for which the red line is right in the middle, then I've essentially fit the graph, right? And that's the kind of model you're going for. You'll notice that sort of philosophically that's a little different than rejecting a hypothesis. What you're doing is you're fitting a model. And so it might be that another set of variables I could pick would fit the model also as well. And so then you have to find a way to distinguish those two models. But in theory, what we're trying to do is come up with a way that we can fit that model. Right? So the other obvious, this is the next set of lines are just if you don't like the ggplot histogram, try that. This is me learning how to do different kinds of histograms in R. So there you go. So that's literally the exact same thing we had a minute ago. So now let's try doing it with a slightly different kind of conditioning. Let's think about the degree distribution, right? So now we can imagine a graph. Go ahead.
Are you going to show the statistical difference between observed and the distribution?
No, this is a non-parametric test, and so what you do, the way you would evaluate statistical significance in this model is you'd say what proportion of times are the observed values greater than because it's a positive number in this case, in which case are the proportion of ties that I've observed in the random graph greater than what I've observed? That's 0. So if because I only ran 500 cases, that means my p-value is 0.002, right? If I had 1,000, it would be 0.0001, right? If it had 10,000, then I'd say that it was 1 out of 10, not even once out of 10,000 times did I get a value that was larger or smaller than mine. And so that's one of the beauties of a probability set, right? Is all you really, like literally your p-value is rank among the observed values you see, put yours in the set, get its percentile ranking, that's your p-value for the set, right? And so in this case, I don't need a statistical test. I can see there are no cases that are smaller than, or that are bigger than the one I observed. Does that make sense? Okay. Thank you. That was, it's an obvious question that I probably should have answered. All right, so again, another way of thinking about these kind of randomized graphs is to think about the degree sequence. It turns out that StatNet doesn't do that, so we're going to do a quick switch and go over to iGraph. I didn't want to detach StatNet and then reattach iGraph and do it, and so what I did is I just called an iGraph function inline. And so I said, for a minute, pretend you're just looking at iGraph. That's what this iGraph double colon thing does. And so given that I'm in iGraph, so use the iGraph function sample degree sequence. And these are the tools that allow you to sample degree sequence. I'm going to encourage you to go and look at the code book to see how they, what all the sundry options that are there. The one that took me forever to figure out late at night when I should have been doing this is that the default method is to pull out a simple graph, but you have to specify simple, no multiple. Otherwise, what it's going to do is it's going to give me and Peter 6 ties between us as opposed to 1 tie between us and distribute those other 5. So you have to restrict the extent to which you can have multiple ties on top of something. Otherwise, you end up with graphs that really look wrong, right? So we're going to do this. We're going to create we're going to say that the out degree for that we're generating for our network is equal to the observed out degree in our real network. That's the vector we created before. The in degree is equal to the observed in degree, and we're saying simple, no multiple. This degree sequence randomization is exactly that zipper method I told you about this morning. So it's going to generate a series of out degree stubs, a series of in degree stubs, randomize them and put them together. So it's not going to check for self loops, right? It's going to check for multiple ties, and it's going to throw away the cases that don't work, but it's not going to check for self loops. And so it's going to be a little bit off. So you got to just be aware of that. I do that, and then I run the transitivity on this piece. It's only about 14%, just on one random draw. So the degree system from one random draw gives me about a 0.14, which is over here. And so then again, let's just do. That's what this random graph looks like, if you want to see it. So again, this code should start to look pretty familiar now. This is that exact same cut and space code, except for now what I did is I put that little iGraph random draw in this line instead of what was either the RAND uni line or the RAND mixing line, right? Do it again, see if it fits, generate a data frame from it, get a histogram, see where you fall. In this case, again, the degree sequence by itself can't account for the amount of transitivity we see in this network. Now, the obvious logical thing you would do if you're a reasonable person would say, well, Moody, of course the degree sequence isn't doing it because you already told us the mixing function has a lot of it, so why don't you do degree and mixing? That's really darn hard to do those kind of things simultaneously. So there's a limits to this kind of fit a random graph model sort of approach, just because the algorithmic challenge of getting a valid draw from the distribution of random graphs is really hard. And so this is what prompts us to do these more parametric-based models, like the ERGMs and such, is because we want to control for more than one thing at a time, right? It's not trivial, but it's pretty easy to control for mixing, to control for degree sequence, and so forth. But to control for mixing and degree sequence, it's just a lot harder and a lot easier for your mixing algorithm to fail. So if you want to do it right, it's a lot harder to do it well. So that's just a way of thinking about this. So what we want to do now then is move on to the parametric way of doing the same kind of model, which is to think about these exponential random graph models. Jaemin, should I just keep plugging ahead on this and then we'll come back to diffusion, or do you want to come back to diffusion? What do people want to do? Let's keep going with this. All right, we'll keep going with this, and I'll try to leave time to Jaemin. All right, so we'll try not to do it too well. Because I'm an old fart and can't help myself, I'm going to do something new now, so I'm going to throw away a bunch of stuff that we're not going to use later, so that's what this cleaning up stuff is doing. I'm just deleting some objects from the graph that we don't need. It's telling me that I've tried to delete something that's not there. That doesn't surprise me. It's because I did this code way too late at night. And so that's all that's telling us, right? And so it's a warning, you're doing something stupid. All right, so let's think about the simplest model we can estimate is an intercept-only model, right? So we're going to walk through the building of an ERGM model. So the simplest possible model is, if we say we're going to generate a model which is a Bernoulli random graph, which is an ERGM object, we're modeling the graph as a function of edges, right? So edges is equal to intercept. That's all it is. So this is an intercept-only model. It runs really fast because it's nothing to it. And then I say, give me the summary of the model, right, which is what the summary function does. And this is what the model looks like. And so this is the simplest possible model you can do in an ERGM framework. And so what I've done is I've said I've estimated the log odds of a tie in the graph. It's minus 2.72. It's statistically significant. That shouldn't surprise us. It's not interesting, but it's true. And what we're telling us then is sort of some basic pieces on the AIC, BIC. It's not a particularly a great model, of course. But what is it actually telling us? Well, since this is a log odds feature, we can convert that to a probability using your classic, the classic probability formula. And so we just exponentiate that, divide it by 1 plus the exponentiated value, and it gives us the value of 0.06. If you ask what's the density of this graph, you'll see that, where to go? Density that, lo and behold, is 0.016. So the only reason those two things are different is that I got lazy and didn't put out all the digits, right? And so this is just another way of saying that what ERGM is going to do is it's going to say, I'm going to generate for you a bunch of random graphs that match your observed graph on whatever parameter you give it. I gave it one parameter, which is density. And so it's going to generate a random Bernoulli graph with a density that matches the observed. And so we might try to figure out whether or not that model fits the data very well. Maybe it does, maybe it doesn't. But what we can do, there's a bunch of built-in functions in the ERGM package which are goodness of fit. That's what GOF means. And so we can say, let's give me the goodness of fit for this random model. Right, that's what's in the first parentheses. I'm going to plot that thing, and I'm going to try to plot that thing. This is the piece that it takes a village fixed for me, right? Because in fact, the plotting function has an error under it. The plotting function has an error that you're never going to see until you try to do a markup down of it, and then it's going to like crash, and at 2 in the morning, you're going to write all your RAs and say, help, I'm failing, and they'll fix it for you. So this is what that's why it says try. You don't need to have try, and in the base code, I'm not sure that it does. And so what the logic of goodness of fit in ERGM is that if your model effectively fits the network, then it should not just fit the parameters that you gave it, but it should fit other features of the graph that you didn't give it, right? And so what that's saying is, I've identified the features that control the construction of this graph, and anything else left over is random noise, right? And so that's the logic that we try to do, is we simulate from that graph, and we compare something like in degree, which is not in our model, to the in degree we observe. And so these box plots give you the distribution of in degree from 1,000 draws of the model that you've generated. So that's the posterior distribution of the scores from the model. And this is what the observed in degree distribution looks like. And because this in degree confidence intervals are so big, we fit pretty, we do actually fit, but qualitatively, we're not actually sort of fitting near the middle of that distribution. So you might want to try a little bit harder than just a random graph. Out degree, same kind of sort of miss. The edge-wise shared partners, which is a really complicated way of saying that if you and I share a tie, do we also share a third party, i.e. how many closed triangles are there? Miss that miserably, right? So this is the distribution that is generated with a random graph. This is the distribution we see. So this is just a pretty cumbersome way of saying that we're not fitting this graph very well, right? So we miss on every default statistic that the goodness of fit piece fits. If you go and look into the manual and the goodness of fit statistic sort of part of this ERGM models. It gives you geodesic distance and shared Wise partners and such by default, but you can ask for any stat that ERGM calculates, you can ask a goodness of fit on. So you can specify your own particular goodness of fit if there's something you care about in particular and fit that instead. These are just picked because they're nice generalized summaries of the graph. All right. So let's add some things to this network that we might actually care about, right? So in this case, we're going to call this our homophily model. And so that's going to be an ERGM object on the graph that we care about with the function of edges. And it's going to have a node match feature on sex, a node match feature on grade, and a node match feature on smoking. And so these are substantive variables that we picked in the data already. I'm just doing to say that this is going to add one parameter to the model that says if we're same sex, what's the increase in the likelihood of us having a tie. I could say node match sex, comma, diff equals true, and that's going to give me one parameter for both male, another parameter for both female, right? I could do another one that says node match mixing matrix. I think it's node mix matrix. I have to look it up. But I could say let's fit a separate parameter for male-male, male to female, female to female, male to male, right? And so you could, so the homophily matching, there's lots of opportunities to do it. This is the simplest non-stupid thing to do, is to just say let's just treat it as one parameter on gender. That makes sense? We did it for race, we did it for grade. Following? Making sense? Awesome. Run this model. It doesn't take these models work pretty well because these are you'll notice that the MC-MC chain here is 0. It's not actually doing an MC-MC chain. It doesn't have to because these are dyad-independent models. And dyad-independent models, the pseudo likelihood that comes out of the logit is perfectly reasonable. So it just does a pretty basic MLE fit to it, and that's what it's using. And so again, now we find that we have the density parameter, that's what it was before, and we find statistically significant matching on sex, grade, and smoking. I would believe those two because they're effectively real. Someone might have made this one up, so this is there. But what you're seeing then, right, is that this is, because it's a positive coefficient, is telling us the log odds of a tie between two people increases if if they both happen to smoke, or if they both don't smoke, right? And smoking is the kind of thing that being an active smoker probably does generate ties, but being non-smokers probably doesn't generate ties. So this is one of those cases where I'd want to use a diff equals true statement if I were really modeling this, because I want to say that it's a differential probability, like it's more socially efficacious that two smokers come together than if the two non-smokers come together, because it's a rare deviant activity. Right? Notice the BIC and the IC, we're going to come back to that in a minute, but just so this is the model fit, right? So this is telling us that's a number that we can use to compare to other models. Does our model itself get any better? The in-degree distribution, maybe we're in this tail at least a little better than we were. We still got this weird bump down here. It's partly because this is a small network. It's a hard distribution to fit. Out degrees gotten much better. We're much more near the middle. We're getting a little bit closer to these edgewise shared partners, right? So we still have many fewer empty triads than the model predicts, but we're doing better at the tail of the distribution. And the geodesic distance matrix, we're still missing that pretty well. So there's a lot of shortcuts in the real graph the real graph has a longer distance between cases than we observe in these randomly generated networks. So the average distance between pairs is much shorter in the simulated network than it is in our observed network. All right, so you can see how this is going to go. We can add different parameters. We can get going. I encourage you to play with this. In the interest of time, I'm going to show you a couple of them. This is the classic P1 model where I add a unique effect for each sender and each receiver. Right? And so what that does is it says I'm going to treat Molly as a particular person, and Peter as a particular person, Joe as a particular person, and their row is going to be modeled independently, and their column is going to be modeled independently. So I'm going to add a bunch of parameters, right? And so if you look at your outcome, you see I get a parameter for each person who doesn't have a 0 row or column in their data set. So these infinite ones is saying this person probably has 0 out degree. This is a sender effect, so 0 out degrees are going to be unestimable. But otherwise, you get a parameter for every person in the network twice, right? I have a sender parameter and a receiver parameter. And it turns out that this is going to improve the fit of the model really well. Like we're going to match the in degree, we're going to match the out degree, we're going to come really close on the triads, and pretty darn close on the geodesic distance, but at a cost of almost tripling our BIC, right? So the model fits, right, but it's not a parsimonious model. And so if your goal is just to throw something in there that fits, this is probably going to work, but it's going to come at a really high cost of doing something that's scientifically interesting. And these are that's useless, but it's there. The goodness of fit always gives you the parameters you put in the model. So it's going to give us a box plot for each sender and receiver in the model. Right? So that's what that is. So we can do some other things. So if the reason we put a fixed effects in this case was because I wanted to account for volume features. So instead I could do this in degree and out degree. That just allows us to treat the volume of ties sent as opposed to the fact that this person is a unique parameter that we're going to fit each time. Lowers my number of parameters dramatically. You'll also notice that I added a mutual tie, and as soon as I did that, my dyads are no longer dyadic independent, and I now have to do an MC-MC chain to get this thing to estimate in a way that's unbiased. And so that's what all these terms are. It's going to go through and it's going to figure out how it's going to step through the space and give us an answer on that set. Again, summary. In this particular graph, we find that the node match protectors are exactly what they would before. The in-degree and out-degree parameters almost have to be significant, right? And what you're doing is you're fitting the row marginals. So if there's any variance in your table in row marginals, this is going to be true. And the mutual effect is also true, right? So it means that there's a higher reciprocity in this graph than we'd expect by chance. And again, you get the same set of fit statistics and all of that. So now what we'd like to do, so I gave you some examples of how you can do mutuality difference by gender. I'm not going to talk about that in the interest of time. What I am going to do is talk to you about how these models explode. So there's a problem I got to be careful how I say this. It's really easy to write a bad model, right? And so people often blame ERGM for being finicky, that somehow the program doesn't work. What you should really be doing is blaming yourself for writing a bad model. The model does a really nice job of doing what you tell it to do, but it's really hard to tell it the right thing to do. And this is that specification issue I told you about before. And so if you try to estimate a model, and this is the one that's greened out here, where I say, just give me the random graph where I have edges, some match features, and a mutual effect, and a triangle effect. So I want to see if there's a friend of a friend should be a friend. If you do that model and try to run it, it's going to tell you, chug along, chug along, chug along, not improving, chug along, not improving. This model sucks, I'm stopping. Right? So essentially the code will tell you you can't fix this. It didn't used to do that. And in fact, I had to write Martina just a couple days ago saying, look, I'm trying to show them what a bad model looks like and I can't do it anymore. And it says, yeah, we know, we got tired of people complaining about it not working, so we put some checks in to say, nope, this model isn't any good, go back and re-specify your model. And so what I've done in order to try to get around it and make it work is I've set up this max iterations equals 2. Right? Usually you'll go up to 20 or 30 of these sort of restarts, and my hope is that I can trick it into stopping, right, before it realizes how bad model it is. And even then, if you try to run this, you say you'll notice it's telling us that the MLE did not converge after 2 iteration. It's going to stop and so forth. It says this evaluating the log likelihood at the estimate. It's sort of it's not doing so well. But when you look at this model, and this is why it's problematic. Before they fix this, if you just look at this model, there's nothing on the face of it, of the results here, that looks bad, right? I get a positive coefficient on transitivity. That's what I would expect to see. Positive effect on mutuality. All the rest of these effects are about what I would expect. Statistically significant, not completely crazy BIC. Like things are doing what we would expect. And then I look at the MC-MC diagnostics, and what you're really looking for in an MC-MC diagnostic is randomness. Right? What you don't want is high autocorrelation. You don't want these ski plots to be like, off onto some weird space or something. And then if you look at the simple statistic cross correlations, and you see that I'm getting a correlation of 0.999 from one set to the next, it's a bad MC-MC chain, right? So this thing did not converge anywhere close to where we want it to go. And you're seeing that because you have super high autocorrelation between the steps in your chain. And you don't want that. Right, and so then here are the simple cross autocorrelations. Again, right, so these things are just not going to where you want to go. And if you look at the plot of your MC-MC chain, that's exactly what you don't want it to look like, right? Instead of being a nice little bottle brush of all random, it's like a bunch of density in one spot, bunch of density in another spot. If we let this go long enough, it goes bunch of density in another spot, bunch of density in another spot. and it just would never give you anything that you wanted to see, right? It really is, that's the signature of a bad MCMC chain. Now part of this looks bad because we didn't let it go very far, right? We usually go like many times further than this, but you'll see that same kind of a pattern, that is if you see any pattern, as opposed to just random noise. And let's see. If you really force it to be mean, I did this on my other machine just so I could show you what this looks like. This is the model. You can then sample from these kind of models. Is it going to let me zoom in on that? Right. And so this is the predicted graph from that model, right? It's just, this is when I say that the positive coefficient on transitivity just snowballs on top of itself, and you get this jump of a clique that is completely unrepresentative. The problem is, if you were to simulate 1,000 graphs from this network, you'd have just the right balance of complete cliques and empty graphs that your density would be right. Because the model will always fit, right, the observed statistics to the graph. Just like the mean of your x and the mean of y in a regression line always intersect, right? The fit statistics will always be the same. It's just that any instance of the graph will be nonsensical. And so that's when you know you have a really poorly specified model. And that's why every once in a while you want to do something like just sample from the graph and generate an image and make sure it doesn't look stupid. Right? That's the goal. A lot of what we're doing in here is the big lesson of this week, if you're sort of at the, this is the final about here and am I done, is be creative, like use your theory to predict your measures and don't do something stupid. I mean, that's kind of the goal of the day. Where'd my thing go here now? All right, so that's so there's some other pieces on ERGM here. I want to just quickly sort of tell you what else is in this sample plot. So this is what a good MCMC chain looks like, right? So this is contrast this to the one we saw before. It's just random noise, just white noise, nice normal distributions. These are the things you want to see out of these kinds of curves. So those are just, aren't they just beautiful? Make my heart sing to see these kinds of things. This is what a sample graph from that model looks like. And again, the fit statistics now are starting to find their way. It's a little bit, you got to be a little bit careful here. This is a pretty narrow range, and so this looks a little wider than it is, but the model is essentially predicting a very simple graph. So it's, that's part of the reason we're getting this right. We've now managed to hit the edgewise shared partners, right? So that's come up right, and our geodesics are getting better. All right, so that's the world's fastest introduction to running ERGMs. What you really should do is go home and play with it, run some of those and see what they look like. The code that you have in front of you also gives you examples on how to run a latent net to these latent net models we told you about before. This is and so I've just pulled the latent net function in. As it normally does, it gives you the features, but I wanted to show you just what these models look like. It gives really nice output, right? So in this particular case, the exact same graph we did before. All I'm doing, where'd it go? Yeah, here we go. Say the latent fit is just a very simple latent model. The graph, I'm going to use Euclidean distance of dimension equal 2. So this is just fit a two-dimensional latent space model to it and see what we got out. I put the start and run time over here just because you're going to be amazed at how long these take to run, right? So this is run on a on my laptop is that's about 32 gig of RAM and 8 processors. So this is not a small machine, and it takes over 2 minutes to estimate a model. On almost 2 minutes to estimate a model. 1.5 minutes to estimate a model on 71 nodes. And timing is not linear, right? So if you're going to run this model on, I don't know, a graph of 500 or 1,000 nodes, submit it and go home, right? Because it's going to take all night. But this is the kind of thing you get out of it. And if you look at this layout should look kind of familiar, right? So this layout should look a lot like the Fruchterman-Reingold or the MDS plots we did yesterday. Because the two-dimensional latent space really is an MDS solution. Those two things are almost equivalent. And so it's going to be rotated or flipped, but it's essentially what you have. And again, the nice thing about this model is you can then go through and add in all sorts of different features that you like. And again, going too fast, zipping through this, same kind of features. You can go to 3 dimensions. I don't care about that for now. Here's one that's kind of fun. You can fit the model. Now I fit that model with 2 dimensions and 5 groups. to give it 5 groups. And this is you might want to explore your data first and see how many groups are in the network. We learned yesterday there were 9, so 5 is probably not the optimal fit. But you can see what it's doing, right? It's giving us that layout, but then it's also saying that these nodes that are in the red have a little higher probability than we would expect just giving their distance in the latent space. Finally, the thing you can do at the end of this is you can add, if you don't care, you might be the kind of person, it's perfectly reasonable, I'm not judging, the kind of person that doesn't care about transitivity, doesn't care about reciprocity, doesn't care about the network structures, really cares about homophily, really cares about treatment effects, really cares about things that you've done in your program. So what you want to do there then is you want to fit your graph in the same way, and you want to put the things you care about, right, as observed statistics, such as homophily on grade or homophily on sex, and let the rest of the graph be fit with the latent space, right? And so I'm just going to say, I don't know what the structure is, I don't care what the structure is, let's just soak up that variance with the latent space and see if there's anything left over to be given to homophily on grade and sex. Now you're giving yourself a tough test when you do it that way, right? Because some of this stuff that goes into the latent space is probably really due to prior sorting on sex and grade, but it's at least a conservative test of whether or not there's anything there. And in this case, it looks like, in fact, that we have a statistically significant effect of grade homophily above and beyond what we see in latent space, and a non-statistically significant effect of sex above and beyond what we see in the latent space. Right. So that's just an example of how you might do that if you're looking at these kinds of models in the latent space. That make sense? All right, in the last 45 minutes, I'm going to let Jaemin come back up. Is your machine working now? Awesome. I'm going to go over some of the diffusion features while he's setting up. Questions or comments about the statistical modeling bits that we just went through. There are some great online tutorials. I strongly recommend you get them. We now have 3 years of different ERGM code examples up on the web page or in your Dropbox. Pull those up, play with them. Try it on school 1, try it on school 5, right? Try it on some different things and see what you can get out of those to get some experience fitting these models. And you'll learn a huge amount once you do them. Yeah.
I guess one question I had, so in all these formulas, G is the wide variance, so the graph itself is what we're trying to predict. But I guess it's the probability of the edges.
So, yeah, I mean, you interpret it as the probability of the edges. I mean, that's if you can. The easy way to interpret the coefficients is that for a 1 unit change in the coefficient, you get that increase in the log odds of a tie between 2 ties in the network. So it's just like a logit model. Technically, what you're doing is you're saying that the odds of observing this whole network, given the set of all possible networks conditioned on the probabilities on the parameters that I put in my model, is that probability set. So the actual model is fitting a whole network fit, but it's much simpler and more intuitive to interpret it on the edge dice instead of what we use.
So I guess I was trying to think of how you might use this to then predict if one of the pattern of infection in the node or something like that.
Right. No, so that's exactly what we're doing tomorrow. So this is 1/2 of that kind of a set, right? So the Sienna models that David's going to talk about tomorrow are essentially a combination of an ERGM model and a linear autocorrelation model. So they treat it as a 2-step model where we simultaneously fit the graph, and the bugaboo, of course, is that sometimes the edges are a function of the thing we're trying to predict, and this model balances those 2 out, right? So that's the goal. All right, you already have a mic. Yeah. All right.
Okay, sorry for all the technological difficulties. So I think my laptop is okay. So let's proceed. So I think everybody got the animation that we produced in this code. So let's open the code again, and let's get into the part 2. Dynamic network safety model. So that's on line 124. So part 1 was just purely simulation from the scratch code. But in some research areas, such as epidemiology, the simulations are so established, so they have certain parameters of interest. So epi model is such an example. So it has all the parameters that are essential for the epidemic simulations built into the package, which is called epi model. So those who have not installed these packages, so please install the API model and NDTV, and let's library them. So even though this model is specifically for epidemiologists, but it has really dynamic features that we can learn from the model, whatever you work on. So it's really useful learning tool. And also, like this lab. So what is like what does this model do? So as in epidemic is susceptible, infected, susceptible. So it's typically the example comes from like bacterial sexually transmitted infections such as gonorrhea. So person infected from the sexual contact with an infected partner then recover from that infection either natural clearance or through some medication. So that is the SIS model. And before getting into the go deeply, so it estimates networks using ERGM models that Jim presented. And also it has some function for dissolution. That's a different part in this epi model. So they estimate networks first, then continue with the dynamic network changes. And especially here, it's not friendship, but it's romantic relationships. So it's all directed because the sexual contact is always a reciprocal. And estimate the networks, then based on that, we spread the disease and how much like this kind of dynamic between networks and disease diffusion just co-evolve. So that's the goal. So here, we kind of do the same. So we set up the number of nodes, like 50 nodes. And so this, I think you're familiar with network initialize function, which is from the standard package. So let's just initialize the networks. Then if I plot them, just empty networks. So we're going to begin from like these networks, and we estimate kind of networks using this model. Then next step is to specify formula, just like Jim did in his ERGM model. So this is very simple. So formula is our sexual networks will be just formed by two parameters, how dense they are and how frequently people cheat on. So because like concurrency is kind of a key parameter in epidemic research. So our ties will be formed by the edges and concurrent function. Then we set up sort of like target statistics because we want to know like how many ties we're gonna make in the networks and how much like they cheat on their partners. So so these two things, so we kind of set up like mean edge one because like people just usually have just one partner, right? So we set up that mean edge, then we set up like 22% concurrency going on these networks. So we create object called target stats for these two parameters. And another parameter is duration. So this model sets up the duration of the sexual partners. So we just have set up this arbitrary number 10 here. So we have such like simulation time like hundreds, but their duration is just 10. So we set up that like coefficient for dissolution. So we then we have set up all the basic parameters. So we have the formation formula and target stats and also dissolution parameters. Then we use net east function to estimate that kind of networks based on our target statistics. It's very similar steps that you have seen all the slides from Jim's lab. So we have the network estimation. Like I said, we have such networks that it's time to spread all the like sexually transmitted disease. So it has like three parameters. One is infection probability, just like we did like for dyadic transmission probability in the first simulation. And also we have the act rate. But all these things just like how much people have sex with their partners. And we also have the recovery rate. So this is model that suspected, susceptible, then infected, then recover. So we set up that parameter as well. But in terms of in the purpose of this lab, we just set it very low so that we can see that kind of like simple diffusion process over the individuals. So I got parameter set using param.net function. So we set up like the 0.8 infection probability with activate 2 and recover only just 1%. And initial seed, we just, out of 50 nodes, we set up like 2 states. And control is just like we specify the number of steps that we take in the simulation. We set up like 30 steps. And like we specified, then people have just 10 times duration over like 30 total steps. And netsim function is simulate all this with all these parameters. Then if we plot them, we have such results here. So blue line is susceptible states, and the red line is infected. So based on this, like the network formation and setting up the infection parameters, so our population of 50 individuals have this kind of endemic. But from this, we kind of know like, okay, so this is like diffused this way, but we don't know yet about what happens to that. So we also have to visualize. And this like epi model package has great tool for that. So we get network first from the simulation. So simulation has the sim object has such like slice by time all the networks. Then these parameters all the bits for the visualization for each time point. So it's slice parameter, render, and plot parameter. And we put it all together using compute animation function. The next final step is the render D3 movie. So this is part of the NDTV package. So I think you can also use for your kind of networks after this kind of process of getting slices together. If you executed that, then it just calls up the dynamic visualization. So we start from the, as we specify, the 2 nodes infected. Then we can begin like on and on. So we can see that how the disease diffuse. You can focus on the red nodes. And gray focus will be that who's cheating on. So because like we set up like 22% cheat. And as you see closely, then you can see like how the concurrency has an effect over the diffusion processes. So because like, this is too fast, but you can set up this point here, then slowly investigate the process. So we have 5. So still like these guys have concurrencies. This task because this guy has like 2 sexual partners at the same time. And they infected it. And also this concurrency here, but they break up. So concurrency not always like the increased diffusion because they also break up before infected. You see like large clusters. So this is very susceptible population when it's really has cluster of relationships. Then it gets really diffused. Like you see like how much fast it diffuses after clustering. Just over 3 steps, this cluster has all like the sexually transmitted disease. So by this way, you can just visualize epidemiology model or your network's dynamics. Okay, so this is I think single time point simulation. then how much does concurrence matter? So we can simulate multiple times, only varying the concurrence parameter. Then we can know with holding all the parameters same, then we can know how much the concurrence matters. So I'm going to conduct like 3 simulations varying the concurrence level. So this time I go with just N500 to make the predictions more stable. And it's all the same steps. So we set up, we initialize networks with nodes 500, then all the parameters like the duration of the relationship and dissolution coefficients and such things like that. And we set up time steps 500. But it's going to take some time because we increase the network size as well as the time steps. So the first trial, as you see in the formula, we only have edge parameters here. So we didn't specify the concurrence parameter. So then the second condition, we include the concurrence parameter here and see how that affects the diffusion. And here I set the concurrence parameter like 50%, 15%. Then for the next simulation step, I'm going to increase that parameter. So everybody's following the course, right? Yeah, the second step's done, then last step. So here I increase the concurrence parameter from 0.15 to 20. Okay, so the simulation's done. So we have like 3 simulation results. Then let's plot them using power function to divide the screen. So it turns out not like huge effect because so all the 3 conditions have largely the same number of impacted population, but it does increase the speed of it. So basically we have like this much curve, then it's just lifted up a little bit. So yeah, so it's not like huge effect, but we can know like how concurrence matters for the diffusion or the speed of diffusion. Because we now divided the screen like this, so using dev.off function, then we can just clear up the figure deck. Next part is we're going to go into the peer influence model. So you have learned in the morning lecture that we have like peer influence opinion model from Noah Friedkin, and that is the key basic model for later the peer influence estimation. So it's a really basic form of the upcoming models of estimating the peer effects. It just because like the first 2 parts we have covered the epidemic simulation, but it's just automatic contingent process. You know, you have sexual context, then you just affect. So it's like basically binary process 0 and 1. But we also have like the ideation of diffusion, right? So we kind of like influence each other for opinion. So if you have like the conservative opinion, then I have like moderate opinion, then we interact each other, then we just change in a continuous space. So that is the model for that. So just a quick review for the model that you learned in the morning. So let's say I'm connected. So this is Jaemin, and connected like 4 alters. 3 alters, then I don't connect with, let's say like John here. So yeah, so you're not friend here. So basically, we have such a matrix here. So I'm here, then you have like W matrices. This is a relational weight. So basically I'm 0, and because I connected these 3 alters, so I have 1, 1, 1 value to these alters. Then because I'm not connected with John, so the value is 0. Then we have also opinion space here. Let's say I have initial opinion as -1, and all these 3 others 1, 1, 1. So basically, maybe I'm liberal, and the other 3 people are very conservative. And John maybe similar opinion like this. Then what pure influence model of Friedkin does is that we just have the weighted average opinion of others. So if I can calculate the pure influence here, then I weight these others' pure opinion using this weighted matrix value. So, but the difference here is that we just have the normalized coefficients. So because I have 4 others, I just have like 0.25, 0.25, 0.25 instead of 0, 1. So I calculate 0.25, 1 plus 0.25, 1 plus 0.25 plus 1. So this is the weighted average of my connected alters opinion, plus I have my initial opinion here. So this is alters opinion, and I have my opinion here. So, but in terms of the weighting my others' opinion or my opinion, it depends on the coefficient A. So this is like pure influence coefficient in the pure influence model. So if this is very low, so I'm very stubborn, then I multiply this other's opinion with 0. Because I'm stubborn, I only believe my opinion. But if I'm really like attracted others' opinion and I'm really like swing person, then I really value this opinion, then my opinions will go to positive numbers, right? Because I value others' opinion, then I ignore my initial opinion. So that is the coefficient for the peer influence model. So what we're gonna do here, so we load iGraph and ggplot2 package again. Then let's create the opinion space here. So here I just take the opinion like minus and 1, just binary, but it's normal distribution with mean value 0 and 2 issue space. Then if we plot them, this is the initial opinion space. So because the opinion issue 1 or issue 2 has two normal distributions, so it's just like the spread out here. Then generate the networks, that's the second step. So we just use the small world graph. How does it look like? Just like this. So this is a typical small world graph with very tight connection around their neighborhood, but there are certainly like weak ties that go across the neighborhood. But we use this graph because it preserves the degree. So everybody has the same degree in the space, but has different like kind of weak type properties each other. So another way to visualize in here. So basically all the chunks here, but there are certain weak ties going across the neighborhood. So this is a degree distribution. So everybody almost has 4 or 5, so degree is fixed like this. So that's the analytical merit of the small world graph. Then the next step is we need to have an adjacency matrix form of the graph. The next part is to get the weighted matrix of my relationship. But we just simply, because like this graph has just 0, 1, so we just normalize by row. So if I have like 4 alters, then 0.25, 0.25, 0.25. That's the uniform weight of my alters opinion. Then, so this kind of function needs also iterations. So we're going to create the function that has some inputs here. So we have A, which is alpha, is like the peer influence coefficients that I explained. And W mat is the weight matrix. So I just consider connecting alters each with equal weights. And Y is initial opinion that I draw here. And T is the last element, which is the number of iterations. So if you execute this line, then the object space gets it. These 3 lines, so because I was interested in knowing how the influence coefficients affects our opinion distribution in the end. So I use the function, but only varying the influence parameter. So it's a peer influence model high, where I use 0.8 as I weight the other's opinion, and the middle and low here. Because I only specified the 10 times iteration, it's just really fast. Then it saves using the list object OR. So if you specify the number here within the double bracket, then it shows the opinion on that iteration. So this is the initial opinion distribution that you saw. Then what's the next step? So the axis change, but the peer influence model of Noah Friedkin is given really it's almost always converge because as you see in the formula, all this model does is just weighted average opinion, so it tends to converge in the end. So this is just the number 2 step, just only 2 steps. Then we just combine all the results, then make a data frame, then how the consensus level varies by the conditions. So here what I'm doing is to take the mean distance of all the opinions here. Then we just create another variable for time. So using head function, so this is our data set. So first variable is just the influence parameter, and the second variable is just opinion. Oh, no, it's opinion distance. Then if we plot here, so this is the end result of simulation. So it's very simple. So it's not much like complex dynamics going on. So if we increase the alpha, which is peer influence coefficients, up to the 0.8 level, it converges fast, and also the consensus level is much higher than these other 2 conditions. So do you see how the opinion model is going on? So it's very simple. Then because I really don't like this model because it's very sometimes I wonder like what does it mean to be like averaging opinions, because sometimes if we kind of talk each other, sometimes we distance each other and go further like backfire effects, and also there are lots going on. But the beauty of this model is to the specifying this kind of the equation. So our opinion is function of my initial opinion and also my other's opinion, and also we can estimate the coefficients which one is better using observed data. So that's the beauty of this model. And also, this established such a foundation for later models. For example, like network autocorrelation model and QAP model. So this is really good to know. And there are many like mathematical models developed out of these peer influence models. So it's really good for you to dig into more about what has been developing after this model. Okay, so I think because Jim already covered ERGM stuff, so this is kind of old model before ERGM. So it's network autocorrelation and QAP model. So, but this model is so important because before you get into so much complex stuff in ERGM, you can better know about the data using this network autocorrelation and QAP model and in very simple way. Because as you see, the ERGM model has very complex stuff and also it's hard to converge sometimes. But when you explore with this model, it's getting more simpler.
It also answers a very different question, right?
Yes,
So,
yes. Also, like because
the
network
ERGM
correlation model
models
is
do nothing,
predicting my behavior outcome based on the relationship. So that's different question. But I think the Siena model is getting gold standard for that. But also Siena model is also hard to fit. So for example, when you do any kind of research like the relationship between social class and health, what you are doing first is get the bivariate association between the two. And this is the model that you kind of doing similar with the network stuff too. So it's definitely worth investigating. So if you haven't already, install norm-derived package. So this is for the function for network autocorrelation model. Then after you install that, then install library, all the packages that needed here. The next one, so next step is to load up all the ad health, but this is definitely censored data without any the secret information. So so we load up all the data sets. So we need like three kinds of data set. One is the edge level data, the other one is node level, and third one is dyad covariates. So let's see what it is. Using head function, SH. So SH is just edge level. So this is the ego and alter, and it has this like real value, but this is actually the tie, the normalized the tie value. So because this guy, the number one guy, has 8 people in their network, so we just divide by that coefficient. So this value sums up to 1. So everybody's values just set up like this. So using this data set, we create a network object called sFriends. So sFriends, basically, we created a network's object, using the edge level data. Then we assign all the attributes from the node level data. So node level data has these variables, so grade and fight level, whether they are female or male, and wise, all the information. Then we store that information on the network object. Now it's time to assign edge attributes. The edge attributes is simple, so we saw that the normalized value, then we assign them into that tie on the network object. So for dyad values, we only have one, which is the shared club membership. So that is the one. Let's say like S-die covariate. I think you better know like what's OVLPEC. Do you remember? This is I'm stealing your
Probably
code.
overlap.
So overlap, but PEC maybe. Never mind.
Oh, extracurriculars. Yes, that's the number of extracurriculars that they share.
Okay, yeah. So number of the extracurricular activities that each dyad share. So that's dyad level covariate. So we create the network object and assign each nodes their node ID and the number of the shared activities. The next step is select the node level covariance model. So we select female or male and white or not and grade. So this is summary information. The next step is we create the weight matrix from the net object. So this is basically agency matrix with the values from the edge level data set. And what you're interested in predicting my fight level based on the peer's fight level. So because this package takes the matrix form, so we take just fight as matrix form basically, but this is my level of fight. So number one person 1, and the other one has no such fight frequency. Then we have all set. So then we use the LNAM function. Let's see what it is. So this is part of SNA package, so for the linear network autocorrelation model. So basically, y is dependent variable, which is the first one to specify. Then x is the covariance to predict that y object. So as I said, we are interested in my phi frequency based on the others one. Then estimate this model based on the gender and race and grade and peer coefficient. Then summary function, it gives us the coefficient and significance. So here, all the coefficients are displayed, the female and gender and grade. So apparently, the race doesn't create the difference in fight frequency, but female does, and grade also. And we have very high coefficient for the peer effects here. So this is how we know the association between my peer's fight frequency and my fight frequency. And it also gives some like standard stats, for example, AIC, BIC. And also, if you use plot function for these results, sorry, because this is so small, I have to do it again. Yeah, it gives lots of like the diagnostic plot. But the unique thing is the network influence plot. But actually, I just discovered, and I haven't covered yet, but I found an article that I can recommend to read, which is the article title is, it's from Carabas, who developed this package, and it's Journal of Statistical Software. So it has so much information about this model, so you can refer to this. But the gist of it here is that it's so complicated. But it's like mean net influence are designed by green edges, and it's kind of like to give you how much the influence varies by the single node. So basically, I think it's like predicted probability for each edges about the influence coefficients and visualize that way. Then, because the first peer influence model, we only included the individual attributes. Then the second model, we include the club membership one. Take some time. Yeah, but it turns out But Jim, I just want to make sure, so this coefficient is for the club members that share? Maybe you don't remember. I think so, because like this one is this added one.
Yeah, I'm an old man. My eyes just don't work that far back is all. So specification is, yeah, shared clubs, right.
Yeah, shared clubs, yeah. So, but even though we include this, the club members coefficient, but my peer influence is still alive.
The thinking there is that there are two, in the linear network autocorrelation model, there are two sources of peer variance. So there's a direct effect, which is the W1, and that's saying, well, if my peer fights, do I also fight? And there's also a sense in which our error variance might be correlated. And so that the little toy model here is that it might be that our opportunities to fight differ if we share clubs. And so if you and I are both on the football team, we might fight more than if we're both on the chess team, or something like that. And so the thinking was that we can put those both in there and see if it makes any difference. Of course, as it turns out, that the shared clubs effect in this case is effectively 0. All the variance is being soaked up by the peer effect, not the direct peer effect, not by the peer exposure effect through clubs.
Yes, so as we share the common foci, then we have much higher likelihood to be engaging each other in some bad ways or good ways. So that's the idea behind it. Yeah, so this is the key core of the network autocorrelation model. Then we go into the QAP model, so quadratic assignment procedure. So the idea here is that if we have like two networks, then we want to know the correlation between the networks. For example, if we can have like the friendship, and also on the other side we can have like negative relationship, then how much like these correlate each other? So we can like create sort of like dyadic metrics, and we can just calculate the pairwise correlation. But as we said, the significance of correlation we cannot know because it's not it's unique like the dyadic level. So we should have like permutation method and something like that to find the significance. So as we learned in the morning, the permutation is just we randomly the shuffle the rows and columns, but with the degree preserved. So I'm going to take some example here. So let's load this Florentine data. This is very famous from patches data. Then we have, once we loaded the data, then we have two networks. One is the business networks from marriage family. Then the other one is the marriage relationship. Let's see how it looks like. First, like business relationship. So this is the basically network. So we have the different kind of family and how they relate to each other. So here, like Castellani and Barbadori has business relationships. And also, so this is like marriage relationship. So this family has their offspring to be married with other the family. So this we have like two kind of different networks, and we want to know how much they are correlate each other. The function to calculate the correlation without.
Because we want to know if doing business really makes us more likely to get married in this case.
Yes, so that's the context. So basically, how much like they develop their business based on like making marriage between the families. So that's the contextual motivation. So G-core function gets you the dyadic coefficient without having to transform all the adjacency metrics. So we got correlation 371, so which is pretty high. Now this is basic metrics here.
So just to make sure I'm tracking, this would allow us to know that there is some effect of doing business on the likelihood of getting married greater than by chance because we've randomly imputed these but we don't know if it's influence of selection or why there is this correlation.
Yes, but the current strategy is not to estimate the relationship based on the other, but we just want to know the association between the two. And if we have association using G-core like correlation, but we are not certain that this correlation is really significant or not. So that's what we have QAP test to get that significance by permutating the metrics. So so test the correlation. For correlation is using the QAP test, where perhaps how much we permutate the metrics here. So it's very similar idea for like bootstrapping for your significance level obtaining. So here we list the two networks, and this indicates like the just we have the two networks here, and the reps is just how much we replicate repeat the permutation. Then if we just return this one, and it just gives you the significance level, so definitely significant, but we can visualize it, how they do it. So as you remember, we got the coefficient level 0.37, and this is the older values by permutations. So we got this much values from random permutation, but our value is much higher than the permutation value. So that's how we know our correlation of the Florentine marriage and business relationship is much higher than expected. The second, so this is an old example. So another example is to using the AdHealth. And we begin to construct the scale metrics. And what we are interested in is whether I and J have the same smoking behavior and is related to the friendship. So this is just data management. So we have 71 students. This is the addresses metrics from that. And we can use like logistic function as well. So that logit is the logistic function for doing that. And as we specify the null hypothesis as QAP, it gets you the coefficient. So it's a slightly different function, but it does the same thing. So we get this coefficient here. So this suggests that if we are friends, then we smoke together. So that's really simple thing. So this also gets you the p-value here, which is marginally significant here. So we get the relationship between smoking and friendship. And we can add something like grade to have like multivariate the QAP model. But to include the additional variable, then we need to create the array that we can just lay up, smoking and also the grade as well as friends. Then here we on X array we get the friendship information and grade information. Then we estimate another model using that logic. Then it gets you the two coefficients here. So it turns out after including both of them, we have still like fairly large coefficient, but it's not really significant from 0. So that's kind of weird result. But because this data is only like 71 students and it's made up data, so we have some limitation. But this is how we do the QAP model. Not only just one variable, just two variables to the focal networks information. So this is all I got. So any questions?
Can I ask about the p-value? You said it's marginally significant. Mine just says p-value of 0.
The p-value is 0. But it has certain randomness included. So because I had only like 0.06, so it could have some variation. So
that's because
yeah.
you're drawing a random draw
Yes.
of only 100 observations. And so, it's going to be 0.06 in one case, it might be 0.00 in another, it might be 0.10 in the next. Bump that up to 1,000 and you guys would come up with the same answer.
Can you give some kind of power advice? I mean, for some of the kinds of data sets people deal with, 70 is a huge sample. So if you need more than 70 or 100 or 1,000.
I don't have like exact answer, but certainly network size over 100 would get you easier, or like just more significant power. But do you know any answer? Because
Yeah,
I
so
have experience like the small kind of network.
Good pun, though. I like it. No, it's so there are two answers to that. There are two times you want to know the answer to that. So one answer is that when you're writing a grant, like the NIH or nice Ph.D., there's going to be this jerk reviewer on there. It's going to say there was no power analysis, kick it out. The answer to there are two answers to that. The first, so this is why you want to know the answer. In addition to the fact that you might actually want to know if you're powered to actually do what you like to do. But the assumption of whole network analysis is that you have the population. So there is no sampling power question at stake. Right? So it's not the case that I don't have enough observations to find an association. The association I see is the association that is in the population. And so the question is, how different is this from random? And the power there is the number of samples you're willing to draw. And so if you're doing QAP, then you should draw a bunch of samples, right? And so to make sure that you have a really consistent estimate of the randomness afforded by the variability in your population. And so the fact that I have only 1,000 nodes or 100 nodes means that essentially there's a limited number of permutations that I can do, unique permutations that I can do on the data set. They're going to generate unique different combinations of the sets. The limiting feature isn't the size of the data so much as it is that in smaller networks, there's not as many networks to draw. That said, there are over 1 million unique combinations of a graph of 10 size. So it doesn't take many graphs to get you into a very large random graph space. So the power is rarely the problem with these kinds of models from this kind of a simple hypothesis testing setback. If you're going up to a second level, if you're doing like an ad health kind of thing or something like that, where I'm trying to say, well, is there a school level effect between schools that have high racial heterogeneity versus those that don't or something, then your power is the number of networks you have. And so at the network level, even a giant study like Ad Health or one of this study that Shark was talking about with 200 villages, the end there is 200. And so your power calculation is done too. Now, one response that I always point out when people start worrying about power is the problem in sociology and social sciences is not underpowered tests. The problem is overpowered tests and p-value hacking, right? And so the reason we have power calculations, the reason they were invented was because they're invented for clinical trials when you have a potentially dangerous drug and you want to give as little of it as possible to the population in case you kill somebody, but you still want to find out if there's something there, right? So that's the reason you calculate power, is to make sure that you have enough to find something if it's efficacious without having to give them so much that if it's not efficacious, you kill too many people, right? That's not our problem, right? Our problem is generally that we've given you an observed data set, you go loose on it, you run your model 1,000 times with a slightly different adjustment, and you essentially p-value hack your way into finding a solution. So the substantive answer to the p-value problem is to put your p-value your power calculation in the model in your grant proposal, because the reviewer is going to require it. But be clear that you're not concerned about being underpowered. You're concerned about being overpowered, and that's good for what we're doing in science. Most review panels that I've sat on, I found that to be a very, is an honest reflection of it as opposed to a knee-jerk reflection of it, and be clear what you're doing and why. And that can be quite helpful. Tom, you've dealt with that a lot. If you had that.
Yeah, I've had the exact same advice. That generally, we have plenty of power. That's not our problem because oftentimes we're looking at a dyadic structure,
right.
And so our n goes up by n times n minus 1. So, that's not the problem. And I agree with you. Put in the regular. And also, since usually the network part is attached onto something else, you're doing the power analysis for the main outcomes that's being studied rather than for the network component of it.
Please.
Does that explanation change if you're pulling, one of your data sources is Twitter? Because in Twitter, what you're getting from the whole file, like 1 to maybe 40% of the actual total.
Yes, so the question is, does that change if you're using Twitter or some other very large online data set? The answer is no. And it's in part because the power calculation isn't a function of the percent of the population you sampled. It's an n feature, right? So it really is. The central limit theorem goes up by n, not by percent of the population. So you're going to be fine. And this is even unless you're pulling like 15 tweets, you're going to be fine. Right? Please.
So what do we do if we're working with more than one network? How do we do these, and then what do we do if we want to aggregate our results and say across all of these networks, this is what we found?
Right. This is a great question. The question is, what do we do if we're dealing with multiple networks and you want to compare the sets? That's where you do multi-level modeling, and it's a fantastic way. These kind of data are just built for that. So you would essentially do a by-network analysis. And so if you're doing a QAP, for example, what you can do is you can run the model for each network separately. I'm going to store the results, and then use your all the tools that are designed for meta-analysis. You just take those exact same tools and do it on your data. So essentially, you set out to do a meta-analysis where you've generated the set. So all of those tools that are used ex post to do the HLM kind of thing, you can throw in directly into pieces. Now, one thing that's a little complicated is that you'll notice we get a probability value, but we don't get a standard error, right? And so typically what I do is that I will generate, this is why you see all these box plots and Instagrams and things like this of coefficient values, because you don't actually have a standard error on the distribution of the coefficients, other than what you see from the mean and variance of the coefficients as estimated. So unlike a standard meta-analysis or HLM model where the second level is a lot of the work in the second level estimation is parsing out the total variance, the total standard errors to within and between. If you're doing a non-random, a random permutation test kind of model, there is no within and between variance to parse because there is no standard error. It's just a permutation test. So it really is a rank test. Now, what you can do instead is you can use multi-level modeling effects for these kind of features. So a lot of people, when they do these models, will remember. Sorry, this is a longer answer than you wanted. You might not be sure what you stepped into. So the problem with these models from a statistical standpoint is that if the cases are not independent, the estimation of the standard error is biased, and you're usually going to overestimate the significance of your models because there's going to be associations that you're not getting. What you're doing by putting in a latent space or a linear autocorrelation model or whatever else is accounting for that interdependence. And so the real problem is there interdependence that is left over that you haven't already accounted for? And most of the time the answer is no, right? And so if you're including things like a linear autocorrelation model term, or a centrality term, or a block term, these kind of things do a really good job of accounting for that interdependence. And then you can model the outcome just like you normally would. And so what you do is you include your linear autocorrelation term, maybe a group membership term, a centrality term. That's going to soak up a lot of that's going to say that so that if there's a problem left in your model, it's conditional on those features. There's some unobserved autocorrelation that you haven't captured. It's pretty unlikely that there's much left over that's not accounted for those kinds of features. So if that's the case, then you have multiple networks. You might do a 3-level model where you have people nested inside their clusters in the network, and then their network, right? And so those kind of models you can fit with MLN or whatever else you want to do with, and it works quite nicely. And especially if you're dealing with cross-sectional features where you don't have over time to exploit that kind of variance, that's a real nice thing to do. Now, because it just so happens that one of the world's leading experts in multi-level modeling is also the developer of RCNA, there is now an RCNA package for a multi-level model. So if you have dynamic data across multiple networks, you can actually estimate on one fell swoop these kind of models. And if you're really patient and are willing to strap rubber bands around. But so it's not an easy model to fit, but those models are there now.
So in terms of Sienna, so Sienna also has features to include another network features into your covariates for another network. For example, like how much negative relationship facilitate your friendship to another person. So that's kind of built-in nature for the covariates from the other networks. So you can predict one network by the other networks as well. So it just depends on your specification of interest.
All right. Thanks, folks. It was a really
Thank
busy
you.
day. This was a lot. Thanks to Jaemin for the work he's done.
Thank you, Jim.